In this video, we'll look at another application where the exogeneity assumption for all S estimation fails, and this time it will be because of economic equilibrium conditions. The example that we'll be looking at is the demand for hotel rooms. We'll study the demand for hotel rooms within a city. So the population that we are modeling is a population of cities. We assume that we are able to obtain data from this population by sampling cities in one particular period of time. Studying demand is an important topic for researchers in industrial organization, or I/O. They would describe one city as one market. And the sampling scheme, where we sample several markets at the same time period, is what they would call a many markets setting. Let's write down a simple demand model for the demand for hotel rooms. So we have a quantity Q, and let's suppose that this gives us the number of bookings per month. And obviously the number of bookings will depend on the prevailing price. Let's note price by small p, and Q of p will give the total number of bookings that will be demanded if the price is p. Now, p can be any price. Let's say it's the hypothetical price. In other words, it does not have to be equal to the price that we observe in the market. The demand curve traces out the demand for any price that can hypothetically prevail in the market. Let's suppose that the demand curve takes a linear form. Beta 1 is our parameter of interest and tells us how demand reacts to price changes. So if we had put logs on the quantity here and the price here, then beta 1 would be the demand elasticity. I don't want to put logs because I want this example to be really simple, but let's think of beta 1 as kind of the demand elasticity. The error term U here gives the total effect of all factors other than price that impact demand, and it is called a demand shock. And here I want you to think of events that can drive up the demand for hotel rooms temporarily, such as conferences, sports events. Both of these would increase the demand for hotel rooms. There can also be shocks that decrease the demand for hotel rooms, such as a COVID lockdown. In a particular moment of time, we'll have different demand shocks in different cities, and the distribution of the demand shock is described by the random variable U. U being a random variable renders Q also a random variable. Economically, this means that if there are two cities in which the same price prevails, the demanded quantity can still be different because there are different demand shocks in the two cities. For a given city in our population, that is, for a fixed demand shock, we can plot the demand curve as a function of P. Let's plot price P on the horizontal axis. Now, if beta 1 is positive, then we will face a downward sloping demand curve and will look like this. This curve gives the demanded number of bookings at price P. And this could still depend on the demand shock. So to be able to plot one curve, we're evaluating this for one particular city. The way we interpret this curve is as follows. Suppose I, as a research economist, can pick any arbitrary price level P. Let me pick this one. And now this P will be enforced in the market, and we will observe this many requests for hotel bookings. Obviously, I cannot enforce a price, and I cannot choose for which P I observe the demand curve. Instead, there is one market price, let's say it is here, and I will only be able to observe the demanded quantity at this market price. The market price is the price that actually prevails in the market, or you could say it is the factual price. So what this demand model allows us to do, at least in theory, is to evaluate demand for prices that are not the factual price or the market price. Economists call these prices often counterfactual prices and would call this not a hypothetical price probably, but a counterfactual price. Let's go back to the idea that we as researchers can assign prices. If we were able to do that, then we could run a random controlled trial or an RCT. To run an RCT, we assign a randomized price P to each market. If we do our randomization right, then P should be uninformative about the demand shock. Or in other words, the conditional expectation of the demand shock given randomized price P should be equal to 0. If we regress the demanded bookings after randomization on the randomized prices, then this exogeneity assumption makes sure that we can estimate our parameter of interest. Determining the price by randomization would mean that we determine the price outside of the market. So the price would be exogenous to market forces. And you can see it's also exogenous in our econometric sense, in the sense that it's an exogenous regressor. This RCT design is econometrically neat, but it's impossible to implement because we cannot change prices like that. Instead, we will have to use the market price that is determined within a given market, and therefore you can say it is endogenous to the market. And we will see shortly that it is also endogenous in an econometric sense. How is the market price determined? It is determined by market equilibrium. And we'll assume perfect competition. The market consists of a demand side and a supply side. The behavior of the demand side is determined by our demand curve. The behavior of the supply side is determined by a supply curve. And we'll assume that this supply curve takes a very simple form. So it is a deterministic function of P. We could add an error term here, and this error term would represent supply side shocks, but we're not going to do that just to keep things simple. We assume that alpha 1 here is positive, so that the supply side is willing to supply more hotel rooms if the price is higher. So you can think of them hiring additional staff so that they can increase turnover. Or maybe some of those hotels are Airbnb kind of arrangements that are not always rented out and are only rented out if the price is high enough. The equilibrium price P star is the price at which the demanded number of bookings is equal to the number of hotel rooms that suppliers are willing to provide. So P star is the equilibrium price, and it will depend on the specific shape of the demand function, and the demand function depends on the demand shock U, which is not the same for all cities, so it varies between cities, and therefore the equilibrium price will also vary across cities. Suppose that we can observe the equilibrium price and the equilibrium quantity in different cities. In other words, we can sample from a population that consists of the random variables giving the equilibrium quantity and the equilibrium price. For this population, the demand equation implies the following regression model. In this regression model, the equilibrium number of bookings is the outcome variable, and the equilibrium price is the regressor. The exogeneity assumption for this regression model will be satisfied if we cannot predict the demand shock from information in the equilibrium price. This exogeneity assumption will fail. This is because the equilibrium price depends on the demand curve and therefore the demand shock. Therefore, by observing the equilibrium price, we learn something about the demand shock. A nice way to see that is to look at a diagram that shows how demand and supply balance. We put price on the horizontal axis and quantity on the vertical axis. The demand curve is downward sloping like this. The exact location of the demand curve will depend on the demand shock. For a given price, demand will be higher for cities or markets with a large demand shock, and it will be lower for markets with a low demand shock. For now, let's look at one specific city or market. Let's call it omega 1. Our supply curve will look like this, and it will look the same for all markets because we have assumed that the supply is the same in all markets and that there's no supply shock. This was just for simplicity. In market omega 1, the equilibrium price will be the price where demand equals supply, so where the plans of consumers and suppliers or firms align perfectly, and this will be this price. At this price, we will observe an equilibrium quantity given by Q star of omega 1. Under perfect competition, P star is the only price that can exist in market omega 1. To observe a different price, we have to go to a different market. Let's go to a market with a higher demand shock, or in other words, a market where for a given price the demand curve is shifted up relative to omega 1. Let's call this market omega 2. We look at the intersection between the new demand curve and the supply curve, and we'll find the new equilibrium price and the corresponding equilibrium quantity. Moving from market omega 1 to market omega 2, the equilibrium price increased And this was because the demand curve in market omega 2 lies above the demand curve in market omega 1. And why is that? Because moving from omega 1 to omega 2, we were faced with a larger demand shock. A change in the demand shock will lead to a change in the equilibrium price that has the same sign. This is because our supply curve is upward sloping. So to see a lower equilibrium price, we would have to move to a market where the demand shock is smaller. So we have just argued that the covariance between the demand shock and the equilibrium price is positive, so it's not zero, and this will imply that the exogeneity assumption is not satisfied. If there is a correlation between the two quantities, then we can use P star to make a prediction about U. The exogeneity assumption says we shouldn't be able to make such a prediction. Since the exogeneity assumption here is not satisfied, we also know that a regression of Q star on P star probably doesn't give us the desired causal effect of price. But here's another way to see that without going into the econometrics. Just note that moving to a market with a higher price is equivalent to moving to a market with a higher equilibrium quantity. This means there is a positive relationship between price and quantity. A simple OLS regression is just picking up a correlation. Since P star and Q star are positively correlated, we would estimate a positive coefficient by OLS. However, the true causal effect is assumed to be negative, that is, the demand curve should be downward sloping. What we are picking up by OLS regression is the upward sloping demand curve, because what we're doing by looking at different markets with different demand shocks is actually tracing out this upward sloping supply curve. To learn the causal effect of price on demand, we would have to trace out the demand curve. In this context, it's interesting to think about why our RCT design works, well, why it is econometrically sound, even if we cannot implement it. By randomizing the price, what we're essentially doing is visiting the demand curve at different random prices, and that allows us to trace out the demand curve and learn the causal effect of price. In this video, I have shown that due to the mechanics of market equilibrium, the equilibrium price will always be informative about the level of the demand shock. And therefore, the exogeneity assumption for OLS estimation fails. We have an endogeneity problem. The insight that a simple OLS regression cannot be used to estimate a demand elasticity is a very important insight in the history of economics and econometrics. The moment that economists figured this out was probably one of the moments that determined that econometrics would evolve as a discipline separately from statistics. The first economist to write about the problem of price endogeneity in competitive markets was Philip Wright. He wrote about this problem already in 1915 in an essay that was published in the Quarterly Journal of Economics. In his essay, you find a graphical analysis that is very similar to the argument that I presented. The simple and highly stylized demand model that I presented here was sufficient for illustrating the problem of price endogeneity. Price endogeneity is a problem in virtually all demand models. Modern demand models are much more complex than our simple model here and improve on many of its shortcomings. In our demand model, we had these demand shocks that distinguished different markets. These demand shocks were things that are transitory of nature, such as conferences or sports events. And apart from these transitory shocks, all markets were the same. That is not very realistic because you would expect the demand for hotel rooms to be much higher in large cities than in small cities and be persistently higher. So we would like to have persistent heterogeneity between markets. Next, note that we were talking about the demand for a generic hotel room and the price for all hotel rooms was the same. That is not very realistic because there will be different kinds of hotel rooms. There will be very simple accommodations, or there will be luxury resorts, and they will all cost differently. So we didn't have any kind of product differentiation. We assumed that market equilibrium would be determined by perfect competition. This may not be a very plausible assumption. Often we are interested in markets where firms have monopoly power. So a better model would have imperfect competition. And then we also assume that all the plans of consumers and producers are resolved simultaneously at one moment in time. And that is not very realistic because when you make plans for staying in a particular city today, you may not travel to the same city in the near future. So our demand decisions take place in a dynamic environment rather than a static one. Modern demand models incorporate all of these facets, and they can be estimated by using clever estimation strategies that circumvent this problem of price endogeneity.